It's my pleasure to introduce Michael Mickelson, who happens to be a member of our club. He is also a member of the Licking County Amateur Radio Club. And after seeing one of our couple presentations on Windows 10, asked if I would bring that information to their club, because a lot of their members are interested in what's going to happen with Windows 10 and the conversion and all. So I went over, I sat in on their business meeting and what they do beforehand, and when I heard about some of the stuff that they're doing, my brain went, wow, this isn't, because there's a lot more that the ham radio does. So I said, well, Michael, fair play. I came to you and told you about Windows 10. You need to come and tell us about all of this fantastic technology that is being used in the ham radio. Hams have contributed rather widely to communicating technology and community service. Everything from moon bouncing communications to providing communications for the Boston Marathon. Michael is a J. Reed Anderson Professor of Physics and Astronomy, emeritus from Denison, which means he's got all this free time. And so he's going to share with us, along with the 6 or 7 people that are on Zoom. So right now what we're going to do is get his screen on here. So I need to somehow turn my screen off, I think.
Start with again, thank you for inviting me, and I wanted to spend a little bit of time with you today and tell you about the kinds of things that ham radio operators do. We often call ourselves amateur radio operators. And I think John certainly deserves the award that he got today. He certainly does a lot of volunteering that I can see, and I really don't know the club as well as I should. I've been a member for a couple of years, but I suppose you might call me a phantom member because I've only shown up a couple of times.
We appreciate everybody that pays their dues.
Okay, glad to pay my dues. And we've donated a number of computers over the couple of years that I've been coming over here. A little bit more about my background. My background is in physics and astronomy, and I taught at Denison for around 32 years before I retired in 2001. And like many retirements, they often start over again. And I worked for another 3 or 4 years with the college part-time in their honors program. My research interests were primarily in astronomy and spectroscopy, and I was interested in the understanding the atmospheres of the outer planets. So I did research both in the laboratory and at telescopes to understand those atmospheres. What you see on the screen here is a picture of part of my radio station. And over here you can see a winter scene of KD8DZ's antenna farm, such as it is during the wintertime. There's a beam antenna here with a couple of vertical antennas on top and some wire antennas that are drooping down from the tower. So in my discussion today, I'm going to tell you a little bit about the early beginnings of long-distance communication. Well, not a lot, but just mention to you some things about how people tried to communicate over long distances. As you can imagine, in prehistoric times, things like fires and beacons and smoke signals. Native Americans apparently used smoke signals to communicate. In the African continent, drums were used to communicate. And I guess by the 6th century, people were beginning to use some sort of a mail process. And of course, we know what Pony Express mail was back in this country back in the 1800s. And then even in 5th century BC, pigeon post. I guess I hadn't been aware of that. And then maritime technologies using something called semaphore. And then there was a flag semaphore and so forth. And then various kinds of signal lamps were used to communicate over long in the mid to late 1800s, we began to use electrical methods to communicate. So, for example, a fellow by the name of Francis Ronalds, a British engineer, developed a way of using a kind of telegraph that depended on using static electricity. And it was actually quite sophisticated. And it actually preceded the type of telegraph that Samuel Morse used back in a few decades after that. Unfortunately, Ronald's technology using the electrostatic methods didn't really catch on, and in fact it really wasn't all that practical, and it was really the Samuel Morse telegraph that became the more successful, and eventually we had transatlantic cables that ran under the ocean. Then electrical technologies such as the telephone came along in the 1870s, and then wireless telegraphy in the 1890s and into the early part of the 19th century, and then radio. And our present technologies now include, as you know, TVs, cell phones, and all sorts of electrical methods for communication. Something new has happened, and maybe you saw the announcement within the last couple of weeks of a gravitational wave that was detected. And back in the 1600s, maybe a precursor to this, a fellow by the name of Cavendish built a balance system that had a couple of large spheres made of lead and a couple of very small spheres made of lead as well, supported by a quartz fiber. And he was able to see the forces between these gravitational bodies and determine the so-called gravitational constant. And of course that was related to the work that Newton did. Well, if you want to get on the computer sometime and search on the LIGO project, L-I-G-O, which stands for Laser Interferometer Gravitational Wave Observatory. And there are two of these observatories, one in the state of Washington and another one in the state of Louisiana. And these two facilities have observed the interaction of two black holes in space. And that has produced an event which they were able to detect using these devices. Back in the 70s, a man by the name of John Webber attempted to detect gravitational waves but was unsuccessful. But this new technology is quite interesting. Each observatory consists of two laser beams at right angles to each other that go for 4 kilometers back and forth, and they look for a variation in the way the Earth senses these gravitational waves. So anyway, take a look at that site, and I think you'll discover some very interesting information there. Now, here's a rough outline of the talk. I'm not going to go into detail about all of these things. I want to mention the fact that Ford and a number of other scientists in the early 17th and 1800s, Frederick Karl Gauss, Ampere, Faraday, and Weber all contributed information about electric and magnetic forces. And those experiments that were done in those early years allowed James Clerk Maxwell, a Scottish scientist and engineer, to develop 4 equations that basically describes all of the electrical phenomena. And as a result of these equations, it was pretty clear that there was a possibility of propagating electromagnetic waves through the air, through the ionosphere. And Hertz then took on the project. His PhD advisor at the German university that he attended suggested that he look to see these waves. And so we'll talk about that a little bit. And then from there, Marconi took the work that Hertz had developed and used that to make a practical communications device. And then, of course, you all know about the sinking of the Titanic. The Morse or the Marconi transmitters and receivers were used to send out the distress signals during that tragic event. I'll talk a little bit about spark coils and various bits and pieces that are used to make radio circuitry. And then I want to talk about what hams do. One of the basic things we do is we like to talk a lot. So we call that rag chewing. And we like to do experimentation. A lot of the new communications technologies have been developed by engineers and amateur radio operators who are engineers, and a lot of amateur radio operators who aren't engineers have developed this very sophisticated technology. So a lot of experimentation, new equipment, and so forth have been designed by hams. One of the things we do is we like to do contests. Almost every month there's some sort of a contest where you try to communicate with lots of other stations. For example, there's the Worked All Continents Award. For example, you work a ham in every continent and you get an award for that. Or you work a ham in every state and you can get an award. Then community service is a big part. In fact, the Federal Communications makes it imperative that amateur radio as a service is a community service, a service that supports the community at large. And so we do various kinds of things. We do special events communications. So for example, we often have a setup at an Arbor Day at the Dawes Arboretum. We have, in the last 4 or 5 years, we've done an event called the Winter Run, where we provide communications over a half marathon, a track that is run over in Granville. We have nets. We communicate and share various methods of communications and so on. And we have various kinds of repeaters that are used, and we'll talk a little bit more about that. And also we've developed some new technologies. For example, one of the interesting things we've done is to bounce radio signals, communicate with another ham someplace on the Earth, bouncing signals off of the moon. So we'll talk a little bit about that. So that's a long-winded introduction. And so I thought I would show you a picture of James Clerk Maxwell. 1865 is when his Maxwellian equations were first published. Not quite in this form. This has been a form that has evolved over time, but these are called differential equations. We're not going to talk a lot about differential equations, but the first one really represents the work of Gauss. The second one the fourth one represents the work that Ampere did, and this is Faraday's work. So, and this is Weber, by the way. So anyway, these four equations are very instrumental in the development of radio communications. Without this knowledge, we wouldn't be able to do it. So here is an image of Heinrich Hertz. Died at a very early age, you can see at 36, but he was able to make the first demonstration of sending electromagnetic waves from one point. This was a device which had a couple of large spheres which are charged with electrostatic charge, and a spark gap here. Anyway, this turns out to be an electrical circuit, and once this thing started vibrating and the sparks jumping back and forth, it created an electromagnetic wave that transferred through space and produced an arc in this electrical circuit, a very simple electric circuit. This is working at hundreds of megahertz, so very, very high frequency. So that's the first demonstration that Maxwell's equations really worked and that you could propagate a radio signal, an electromagnetic signal from one point to another point. I should mention to you that light is another form of electromagnetic radiation. That's been around forever and ever and ever, right? And so this just happens to demonstrate an electromagnetic signal at a different wavelength. So light is very, very short wavelengths, microwaves are a little bit longer, and radio waves are much longer. So it's all the same kind of stuff, but this is the first time that radio type waves were transmitted. Here's a picture of Marconi and his wireless setup from 1895. This is a typical setup that you would have found in a radio room on a transatlantic steamer. The first transatlantic radio communication was December 12th, 1909, and that went from England to Newfoundland. And the signal, basically the signal S was transmitted, 3 dots, dot, 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 dit, 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 was the signal S that was transmitted from England to Newfoundland. And of course you all know about the sinking of the Titanic, and in those days what is now the standard distress signal, SOS, was in those days CQD, and it was a long time before the people on the sailing ships started using the SOS signal. But that was started by the Germans back in about 1909. So here's some of the bits and pieces that were used in radio. Here is a spark coil. Basically, automobiles I guess still have spark coils in them. They're called electronic ignitions now. But in for example, the Model A Ford, maybe up through my 1970 Pontiac probably had a spark coil in it. My tractor still has a spark coil. But the spark coil has an interrupter that produces a spark gap here, and connected to a coil and an antenna, you can generate a radio signal that will pass through the atmosphere. A fellow by the name of Lee DeForest invented the vacuum tube. Edison was very close to inventing the vacuum tube, but didn't quite make it. But here's a sort of historical representation of early vacuum tubes and more modern vacuum tubes. I should tell you that in this day of solid-state electronics, chips like these, we still have a use for vacuum tubes, especially in high-power radio frequency transmissions. So if we want to generate a 100 kilowatt radio signal, we're not going to do that with solid-state devices. We're going to do that with vacuum tubes of various kinds. These are called integrated circuits. They're based on transistors. Here's some early pictures of the development of the transistor, which was done back in the 1950s. And then here is an application of resistors, transistors, integrated circuits in a very small computer. This, I think, is probably one of the new UNO. You've heard of the UNO computer. It's a little microcomputer about the size of a credit card. And we find these in amateur radio equipment all over the place. And of course, in automobiles, everywhere you can think of needing a computer, there's probably devices similar to these little microcomputers. Well, here's some of the things that hams do. Here's someone having a transmission. See, who uses a computer. I'm not sure where her radio is. Probably this device is her radio. Here's a young ham just getting started in amateur radio. Here's a guy that's hilltopping. He's got a backpack with a radio on it, and he's trying to make communications from the tops of mountains. And then every once in a while, you need a pal on the radio station, and you can see this cat staying nice and warm on top of the radio. One of the neat things that computers have allowed us to do, and one of the neat things that software has allowed us to do, is to do what's called weak signal propagation testing. This is called WhisperNet, and WhisperNet is based on very small signals, like less than 5 watts, that can be transmitted across the continent. And the basic purpose of WhisperNet, it's a real-time net. You can get on your computer and Google WhisperNet or WSPR, and up will come an image like this, and it's real-time, and it will tell you what radio signals are being propagated. Now, the reason for propagating signals at very low power ranges, in fact, down to milliwatts of power, is to see what the radio propagation conditions are in the atmosphere. And so this is really a nice service for anyone, including amateur radio operators and anyone else who needs to make long-distance communications. And you can look at this and that, and you can see what stations are communicating with each other. A Nobel Prize winner physicist by the name of Joe Taylor invented this weak signal computer code that allows for this sort of communication. And he developed it for doing processing of astronomy signals in radio telescopes. So there's a connection between ham radio and astronomy and astrophysics. Joe Taylor. I'm going to click this again. There it is. Here's an example of moon bounce. A signal is transmitted from a radio station here, goes up to the moon, bounces back, is reflected by the moon. You think of the moon as a big reflector in the sky. And of course, you already know it reflects sunlight because you can see it. And so the signal goes up, bounces off the moon, and comes back. Here are some antennas that are designed to do that work. Here's a large disk. And let's see, I guess back in April 2010, we attempted to do a moon bounce experiment and to see if we could detect the station. The station that was being used is the Arecibo, or Arecibo, depending on how to pronounce it, observatory down in Puerto Rico. This station is, or this facility is usually used to look at astrophysical sources, to look at pulsars, galaxies, radio galaxies, and so forth. And here is a huge reflector. This is a big dish that's in a valley. It's about 1 kilometer in diameter. The antenna system is supported by these 3 pylons, and this is the receiver that is used to detect those signals. Now, what we did, or what the amateur radio community did, was to use the Arecibo facility as a source of radio signals, both transmitting and receiving. And so the local Puerto Rico Amateur Radio Club that's associated with Arecibo set up their transmitter, connected it to this huge antenna. It has a gain of 60 dB, which is fantastic. And that's 65 powers of 10, how much stronger it is compared to a regular signal. And so we set up in my backyard, in my garage, an antenna mounted on a telescope tripod so we could track the moon with it. And you see it sitting here by my garage. And here's the radio equipment we used. And KLJ Bob Kanan was one of the 2 or 3 people that assisted in this project. And so we were able to listen to other amateur radio operators who were bouncing signals off of the moon and from Arecibo. They did not hear us, but we could hear them. Our antennas were not sufficient to the task. Another thing we do is we're involved in amateur radio emergency communications. In particular, we have a local group here, a local areas group, and you can see each one of us is certified by the Emergency Management Agency, which is part of Homeland Security. And so we have a number of probably 20 or 30 hams in Licking County that are part of ARES and the EMA. And in fact, you probably remember derecho. Did anybody have any tree damage and power outages during derecho? Probably almost all of us. I was down for about, I was down for 6 or 7 days before I got power back. But we ran emergency communications for the Sheriff's Department, the Police Department, the EMA, and Homeland Security because their systems were down. So we were the only source of communications for about 24 hours in Licking County because of the derecho. It was a pretty amazing event. Weldon Matthews at the time happened to be the amateur radio emergency coordinator. So that's one of the things we do. This is a little example of the kinds of certification and testing and training that we do. One of the other things is preparedness. And one of the issues for preparedness for us is statewide preparedness. And so in April of last year, on the 26th, we set up stations all over the state to make sure that we could communicate with the Central Areas Communications Network in Columbus, Ohio. So we broadcast, again, we set up in my garage. You can see my boat in the background. And Eldon Peterson and myself operated several stations here. This is a specialized antenna called NVIS, and it has the capability of statewide communications. We probably can't communicate California with it, but we can certainly communicate with surrounding states, and we have solid communications around the state of Ohio. We worked stations in 32 counties from our location. Other stations did similarly. So, by the way, this is an antenna design that I came up with so that, in fact, it turned out to be one of the more efficient designs during that test. Most of us in Aries are also part of Skywarn. Maybe you've heard of Skywarn. Skywarn is an organization that amateur radio operators participate in during emergency events. So in 2014, Lincoln County Severe Weather Spotters Net will get together and we go through the process of identifying certain kinds of disaster signs, you know, wall clouds, tornadoes, and that kind of thing. Very high wind speeds. So we go through training once a year to do this. My training is coming up next month. One of the other things that amateur radio operators use, and by the way, these same kinds of technologies are used by the police force and other folks that need to communicate. These are called repeaters. On Horns Hill, we have a very nice antenna to attach a ham radio repeater antenna to. How many of you have been up on Horns Hill? Okay, so that's a very tall antenna. We're at about over 1,400 feet above mean sea level. And that's our antenna location. But the purpose here is in high frequency communications, say at 140 megahertz or 440 megahertz, line of sight communications is all you've got, because the radio signals are not bounced from the ionosphere very efficiently. They go right on through the ionosphere. So at 2 meters, to have area-wide communications, we need to have a device called a repeater, which can take a signal in on one frequency, okay, 146, it comes in on 146.28, and then is broadcast out by the repeater on 146.80. So this is simultaneously. So if I'm in a vehicle over here, or at my house, and I want to talk to somebody else over here, the mountain's in the way, so the signal's not going to get through. But if we have a repeater, this is line of sight. So my 5 watts can do a good job. In fact, my 500 milliwatts, half a watt, can do a good job communicating with this repeater and be received by somebody else. And this distance can be, 50 miles or so. So repeaters are very important in communication. This is the repeater set up on Horns Hill, and its call sign is W8WRP. So there are 2 repeaters, one for 146 megahertz and one for 444 megahertz. Another use of, start talking a little bit about using computers. NetLogger is a real-time logging program that we use. For example, on our nets, when we meet every other Wednesday, we have a net, emergency preparedness net. We get on and one of us will run this program called NetLogger over the internet, and anybody who has a computer can watch and see what the communications, who's checking into the net, and so forth. And in the case that we have an emergency situation, we'll also run NetLogger, and we'll log the communications that occur during that emergency. So a good use for computers. Not a very sophisticated use, but a good use. Another thing the hams like to do is DXing. I mentioned that before. Here is a DX expedition that went to the South Sandwich Islands. Anybody know where they are? South Georgia Islands. They're down in the South Atlantic. It's very, very cold there. Down about, maybe 70 degrees north, south latitude. Very cold. So they put together a team to go down there and to set up many radio stations, and then from that location they try to communicate with people all over the world. And again, it's kind of a competition in some sense to see how many of these distant locations that you can work with your radio equipment. So we've had people do the Sandwich Islands, do South Sea Islands, do all sorts of exotic places where you'd like to set up a radio station. And you can see it was pretty cold there. They have these tents set up, antennas, and here's one of the stations where people are operating. This year, they used to go down to these locations for 2 weeks at a time. So they did 2 weeks in the Sandwich Islands and 2 weeks in South Georgia. And as it turned out, the weather got so bad that they had to curtail operations in the South Sandwich Islands and get back on the ship and move to South Georgia. And they had a very short communications set up there. So sometimes the weather or the conditions get to you and you can't really complete what you want to do. But they make hundreds of thousands of communications with other hams around the country. So here's a little list of things that how computers are used in amateur radio. One of the things that's kind of interesting, we do a lot of testing and building of circuitry in our laboratory, so we need test equipment. Nowadays, there are software programs you can put on your computer with a little interface circuit that you can use to make an oscilloscope, an antenna analyzer, a signal generator, a voltmeter, and so on. So your computer can become a set of test equipments. As I mentioned before, we use it for logging contacts. It can be used to control radios, and I'll talk about a special kind of radio here in a minute. We can use it to hook the computer to our radio transmitter, and we can use the keyboard to send CW, okay, Morse code over the radio. So instead of using a key, a hand key to do the sending, use your keypad on your computer. I mentioned weak signal communications. JT65 is an example of a computer-based weak signal communications technology, and what it has in it is some sort of error correction, so that in very noisy conditions, it can actually dig the signal out of the noise. So these computer programs that Joe Taylor, I mentioned Joe before, had designed. PK31 is another example of computer-based digital communications. PhilDigi is a package that we use here in Licking County. It's very helpful in that we can submit, for example, let's suppose we're in an emergency situation. We have somebody at the hospital, we have somebody out in the field, and we need to send digital information from the field to the hospital. Let's suppose we have some accident victims. We need to send secure private information to the hospital. We can use this program, PhilDigi, which contains a number of programs that allow us to do that. We can also transfer video and image information using PhilDigi. SDR is really a neat technology. In the past, radio receivers and transmitters were fairly complicated machines. They're called super heterodyne receivers. Maybe you've heard that term, but you have to have radio frequency amplifiers, you need intermediate frequency amplifiers, you need all sorts of oscillators and converters. And SDR technology changes that a lot. The RF part, the electronic part of radio receivers and transmitters now is quite different. It uses digital technology, and the software that goes along with that basically controls the device and reads the information out. I'll show you an example. Oh, well, here's a computer program that turns your computer into an oscilloscope. Okay, and these are free on the web, by the way. You can just download them. And then all you got to do is make a little circuit to connect to your computer. Okay, here in the past, I should put up an image of a typical modern radio transmitter. Have lots of buttons and knobs. It'll have dozens and dozens of buttons and knobs. SDR radios have no buttons and knobs. There's a place for your headphones, a place for your microphone, a place for your code key, and an on-off switch. On the back, these are your connections to your antennas, basically, and your power supply. Now, what happens is, whenever you want to use these radios, by the way, this one has its computer built into it, so you don't need a separate computer. So it's all self-contained. Some of the early SDR radios was a separate box, but then you had a plug to your computer with a USB port or an RS-232 port. So this is looking at, instead of just seeing one signal at a time with your radio, you're seeing all the signals, in this case, for the 15-meter band. Each one of these little blips here is a separate communication. Some hand talking to some other hand. Okay? And you see the whole thing at once. It's fantastic. In fact, you can set this up so that you can actually see 3 or 4 or as many as 8 bands at the same time. So you can take your mouse and click on one of these peaks and you can listen to them. And if you want to transmit to them, click your mic and transmit to them. Okay, it's really fantastic. This is single sideband and CW signals, and this is an example of FM signals. So you can see the FM signals are a lot sharper and cleaner in some sense, but the communication is equally sharp and understandable no matter which way you go, whether it's FM or single sideband. Well, the umbrella organization for most amateur radio operators in the U.S. is the American Radio Relay League that was started back in 1915. And by this old brain is, some things fall out of it every once in a while. I can't think of his name. But anyway, this fellow started the ARRL, and it's been basically publishing the QST magazine for over 100 years. We had our 100th year anniversary last year. So I think that wraps it up. So I like to look at amateur radio as being, so far, up to this point in time, sort of the end of the beginning. There's all sorts of interesting new technologies that are being developed, and we don't know where we'll be in the next 100 years. So at this point, if you have questions, I'd like to take some time and answer any questions you might have. Yes?
I kind of feel funny about asking you this question, but my mind is having a terrible time understanding how you know how far a signal is going to go. I mean, how?
Well, actually, that's a good question. Okay. We have propagation of radio signals depends on the atmosphere. So for local AM, if you're going to listen to WCLT, you notice if you get very far away, you can't hear WCLT. Okay? That propagation is by what is called ground wave. Okay? So that's a fairly short range communications. It's low frequency. Okay? And so it doesn't go very far. I mentioned high frequency communications also being short range because those radio signals penetrate the atmosphere and don't get reflected back. But for example, a 20-meter band or a 40-meter band or an 80-meter band signal, okay, 3 megahertz to maybe 10 megahertz, those signals are refracted by the atmosphere and come back down. And depending on the frequency, that determines how high in the atmosphere it goes and thus how far it gets refracted. So 10-meter signals can get refracted all the way around the Earth under the right conditions during the sunspot signal.
But this day and night?
It depends. It changes day and night. So in the nighttime, you can actually have a little bit better AM signal propagation because you can hear WLW down in Cincinnati or WMOC down in Missouri at nighttime, but during the daytime you can't. So propagation a little bit better at nighttime for for long wavelength transmissions. For the 80-meter band, if you want to do long distance communications, best at night. Daytime it's more local, over the state or Pennsylvania, West Virginia, and so on. So it depends on the atmosphere, what it's doing. It depends on what the sun's doing to the atmosphere. And it's making lots of electrons up in the upper atmosphere. That helps in the refraction and the propagation. And we have programs, computer programs, that take this data from NOAA and a number of other sources They give us information about, that we can put into our program and determine what frequencies we can have the best communications over. So if I want to know if I can talk to Greece from my location on 10 meters, I'll use this program and punch in the local data, the atmospheric data, and I'll say, oh, well, I can't do that tonight. It's not going to work. But I'll figure out maybe some other band. 40 meters might be appropriate, so I'll use 40 meters. So computers are really important in what we do, and everything from controlling equipment to making our equipment do certain things, to doing analysis of communication situations. Computers have been very helpful to us.
Yeah. The might help a lot of them to know that back in 1971, you could sit in Newark and talk to Cactus Girl in San Antonio, Texas, and it sounded like she was in the next room.
Yep.
That was in 71.
Yep.
I had...
Was that a CB equipment or what?
Mine was a little CB that got linked in the car or in the house. And when I went to work for a 7037 truck stop, they
Yeah.
said, bring it with you. And during the night when I was working, it was connected to ours garage, and we could report cars on the highway to New York.
Yep. That's 11 meter band, by the way. You have a question?
Yeah, actually, I have three, but they're short. You mentioned about distance of propagation. I remember from Philadelphia, PA, and I remember decades ago at night, I could receive a Chicago radio station called WLS. So I knew all the Beatles songs before they came out here. And I was surprised that the next afternoon it was gone, no signal, but it comes back at night.
Yep.
So I don't know if that was cloud cover or the rotation of the Earth.
No, it's actually the nighttime propagation. The atmosphere has these various layers that sometimes are more active at one time than another. And at nighttime, the AM broadcast band, we're talking about hundreds of meters, okay, of wavelength. Okay, 10 meters is what, 30 feet? Is that right? About right, 10 meters?
Yeah, right.
A little over 30 feet. So an antenna on 10 meters would be on the order of 30 feet long. An antenna at broadcast band is going to be several hundreds of meters, okay? For example, one of the amateur radio bands is on 160 meters, which is 1.8 megahertz, which is at the high end of the AM radio band. And that's 160 meters. So you can see if you're down at 700 kilohertz, where WLW is located in Cincinnati, then you're going to be 300 or 400 meters. So the key thing to answer your question is, at nighttime you get better propagation. I can listen to, what is it, what's the Boston?
Oh, BZ.
BZ, WBZ in Boston at night. It comes in nice and, most of the time, nice and strong.
Okay,
Yeah.
the second question.
Oh,
With traditional ham radio, I'm thinking about licensing and all that kind
Yeah.
of stuff, but with this, am I correct to assume that with a computer, you don't have any of that, you just go on and do it?
no. I didn't mention something called Echolink, but in order to make use of the amateur radio frequencies, you have to be licensed. And now there are three classes of license. There's the so-called technician class license, which is sort of an entry-level amateur radio license. There's the general class, which is sort of in the middle, gives you a lot more privileges, but still limited in some ways. And then there's the amateur extra class, and that allows you to have access to all the amateur radio frequency privileges. So you still have to be licensed. Our club gives testing every once in a while. We're certified by the FCC to do this, as a number of other radio clubs around the country are. We get our licensing through the American Radio Relay League, and we're called volunteer examiners, and there has to be 3 extra class licensees to give the examination. And I know there's some tests going to be up in Mount Vernon here next month. You have a third question?
Yeah, just about the shortwave. Do you know of any way with the computer to listen to shortwave radio?
With the computer?
Yes, they can get European broadcasts, for example.
Well, there are some URLs you can go to that will allow you to say listen to do the BBC, but there are modules that you can attach to your computer and with an antenna, short antenna, that will allow you to actually take those signals, download them from your antenna. Basically, it's SDR. It's a miniature SDR radio. Sometimes they're called dongles. Is that a term that you know? They're sometimes called dongles. Plug into your USB port. And they have an antenna, and then the computer then interprets all that information. So you can do a search on SDR dongles.
Okay.
And maybe come up with that. Yeah.
Distance. What's the name of that group with the radio antennas that's been listening for extraterrestrial communications for about 40 years or so?
Yeah, well, back a few years ago, there was the Big Ear. Am I still coming in okay with this, Mike?
A little bit fuzzier now because it's down here low.
Move around.
That's good.
Big Ear was a radio telescope owned and operated by the Ohio State University. And it was up at Delaware near the Perkins Observatory. And it was a football-sized metal reflector that could be tilted.
Rub it on your chin here. Let's do it this way.
All right, sorry about that.
Oops. Scratching the chin.
Sorry about that.
That's okay.
Big Ear was a term that was used to rename the antenna. It originally was a radio telescope that was used to look for to do a survey. And as the Earth rotated, this antenna would scan the heavens, and pick up signals. And it could be tilted a little bit, so you could look at a certain portion of the sky, not the whole sky, but you could sweep out, as the Earth rotated around, you could sweep out the entire section and circle. But then, its purposes for doing strictly radio astronomy, for looking for pulsars and galaxies and that kind of stuff, that sort of subsided. And then it was taken over by some volunteers, and that's when the name was changed to Big Ear. And they were basically just recording all the extraterrestrial radio signals that they could detect, and basically compiling that information. They had very sensitive radio receivers. Now there's a group out in California that's doing that.
What I'm talking about is continuous. They've been doing it for about, 40 years or so. And they are listening for extraterrestrial. It's not just one radio telescope. It's a whole network of them, and I forget what they.
It's called SETI, right? Search for extraterrestrial.
Yeah,
I
SETI.
don't know whether it's
SETI, that's correct.
Yeah.
Search for extraterrestrial
Intelligence.
or something like that.
So, distance is, it can go on for light years, obviously.
Yeah, we're talking about the age of the universe being, 15, 16 billion light years, or billion years old. And those are huge distances. The Hubble Space Telescope just observed the location of a black hole in a galaxy that's very, very far away. So, radio receivers and telescopes, optical telescopes, can see a long ways. And so far we have not seen anything definitive in terms of extraterrestrial intelligence. But we have a lot of data. We see a lot of things like radio galaxies in that process, and neutron stars and pulsars, but nothing that we can say is extraterrestrial communications. Yeah.
Yes, mine might be a little lower question here. What's the difference between an AT&T tower and one of your towers? And they all transmit.
Well, if you're thinking about an AT&T cell tower, for example,
Yeah, cell tower and one of your towers. What makes yours?
the difference is going to be the antennas and the frequencies that we're operating at. So most of this stuff, cell phone stuff's working at like 600 gigahertz or 600 megahertz. So they're very, very high frequency. Antennas are like that. You know, think about your cell phone. How big's the antenna in your cell phone? So it's going to be basically frequency dependent. The higher the frequency, the shorter the antenna. Our antennas on the...
They're long.
well, it depends. My antennas at home are big, but then I'm on very low frequencies. My beam antenna goes up to 50 megahertz. My wire antennas go down to 3 megahertz. But the antennas on the tower at Horns Hill, the 2-meter antenna, well, the shortest 2-meter antenna you can have is about 19 inches. And if you go to a 70 centimeter or 440 antenna, then it gets about like that. Okay, but it's all in the frequency. It's all in the design of the antenna.
I don't know, is CW used much, and if so, is any of your licenses required to know CW to it?
No, as it turns out nowadays, you don't have to go do a CW test. My first licenses, I did CW. I had to take a test. And that's all gone away. But the interesting thing is, you know, there are 700,000 amateur radio operators in the U.S. 700,000. Wow. There are about somewhere between 500 and 600 maybe in Licking County. And I can't tell you how many have CW capability or not. But if you go onto the ham bands and you listen, you hear lots and lots of people using CW. So it hasn't gone away. Just because we don't require it for the license anymore, there's still people learning CW and making use of it.
I understand even the services don't use CW anymore.
But they're still trained. The Navy has a new training program out to make sure all of its operators know how to do CW. And in fact, pilots are required to know CW at a certain level.
Being an old veteran of the service, I always knew the Navy had the best operators.
Well, they did. They did. In fact, after the Second World War, the Navy wanted to glom onto the entire electromagnetic spectrum and control the whole bloody thing. And it was only when finally, I think it might have been President Truman, or maybe, I guess it would have been President Truman, basically said, look, we've got to go back and see this divided up. I mean, there's got to be public service, like radio stations and TV stations, amateur radio service. So there have to be a variety of different services, not just having them all controlled by the military. But the Navy operators were some of the best.
Yeah.
Yeah.
How in the world did the LIGO people come up with the idea that it was 1 billion light years, 2 black holes collide? I mean, from the signal they got, is there enough information in that signal that they...
Yeah.
What about that signal? Was it the spectrums? I mean, the various...
Okay, here's what happens. In the early days, Joe Weber, I mentioned him, back in the 70s. Joe Weber tried to detect gravitational waves. Now, Cavendish's experiment was a static experiment. It wasn't a pulse, it wasn't a wave. It was basically looking at the gravitational force between 2 objects. In fact, just standing here, the gravitational force between me and the Earth is what keeps me on the Earth, because it's attractive, right? Okay. A gravitational wave is something a little bit different. It's kind of like a radio wave, except that it's in the gravitational domain. Back in 1919, Einstein developed the general theory of relativity. And out of the general theory of relativity came a set of equations not too different in some sense from Maxwell's equations. Very similar to Maxwell's equations in that one of the predictions was that there could be waves transmitted by gravity. Okay? And a fellow by the name of Kip Thorne at Caltech, California Institute of Technology, wrote a really informative book back in early 80s that talked about the general theory of relativity, and it was very widely read and very widely understood. Weber thought we ought to be able to detect these things. So he built a, 1,000-ton aluminum cylinder with strain gauges attached to it so that it would detect a gravitational wave. And what you would expect is a gravitational wave went through and interacted with this cylinder that would cause distortion in the cylinder, and you would see a change in these strain gauges. Now the problem is there's all kinds of other noise, vibrations from the road, people walking by, people sneezing. I mean, it doesn't take much for that sensor to detect those kinds of signals. So he was never successful. He thought he'd seen some signals, but he hadn't. So to get around that problem, you need two detectors. So we have one in Washington and one in Louisiana. These are based on the so-called Michelson interferometer, which uses lasers. And basically, by separating them, local noises are canceled out. So if you don't see the same signal in both places, you know it's noise. You know it's local. And so what they saw was a signal recorded by both instruments.
But after having read the article, when they said 1 billion light years, a number, and from two black holes colliding, an event, how in the world did they interpret the signal that they got on their
As being just two
detector
black
as
holes.
being from that?
Well, if you do a calculation, okay, go back to Kip Horn's theory of general theory of relativity book. When you look at that, and what you discover, basically it comes out of Einstein's equation. In order to detect a signal like that, you have to have enormously massive bodies, and the interpretation of that signal has to be based on huge black holes interacting with each other.
Jamie, will we turn the lights on, Jeff?
Based on huge what?
Based on the general theory of relativity, in order to detect any sort of signal from that kind of distance, it's got to be something huge bodies interacting. We know, for example, that the sun bends light. So that, for example, during the 1919 eclipse of the sun, there were two groups that went, one to South America, and let's see, where'd the other one go? Can't remember whether it was Africa. Anyway, there were two groups that went out. This is after the general theory had been published and so on. They said, okay, we can test this. We'll look at a star field that you can't see during the daytime because the sun's, making so much light. But during an eclipse, when the moon goes in front of the sun, you block the sunlight so you can see that same star field. So at some point in time, when you can see that star field, you take a photograph of it. And then during a solar eclipse, when the light from those stars is passing by the sun, you see their positions on that image of the star field shifted. And that was one of the first detections of the general theory. Another prediction of the general theory is that clocks will run slower in a gravitational field. So if I put a satellite up with a clock in it, it's further away from the Earth, so that clock will run faster. So those were two basic tests. There was another one, the rotation of perihelion of Mercury was not explained by classical physics. And so they actually went to, they had to use the general theory of relativity to understand the difference that they were seeing in the observations compared to the predictions. So it's based on, theory, and I guess that's the best answer I can give you at this point.
Well, it still surprised me that they said a billion. They gave an actual.
Yeah.
I mean, we know 16 billion since the Big Bang or whatever, but how they were able to come up with a billion light year distance,
Well,
that seems very strange. Why not 5?
Okay.
Why not 7.5?
here's an answer that may help. Hubble, back in the guy that the telescope's named after, back in the 1900s, early 1900s. He and based on the work of an astronomer by the name of Schleifer, had observed that the redshifted light in galaxies increased as you went out in space. This event, this gravitational event, took place in a galaxy whose distance we know because of its redshift. So I guess that's sort of the answer. And you know, with light, you know, we can see things that are 15 billion light years away.
So they were able to analyze the frequency of this signal that hit in LIGO too.
Yeah.
Or they couldn't have done what you're saying. I mean,
Well, I think what they were able to do was to pinpoint the galaxy that it was in, and of course they can see that galaxy in light, you know, at light waves, and so they
they
can.
use standard candles or whatever.
Well, it's beyond that, but you know, you look at the redshift of quasars. Okay, so you know, you start off and you get standard candles for the nearby galaxies. Okay, Cepheid variable, and then you branch out to the next candle, then the next candle, and finally the redshifts is your final candle. So once they determine which galaxy this thing came from, and we're going to be looking for some more of these events. You know, this is the last word. So anyway, I've probably taken up too much of your time. So I appreciate your attention. Enjoyed your questions.